Hello. This is our computer vision project for classification of natural disasters for Data 200. Our team was Shawn Schulz, Jerry Milford, and Jesse Maki. We're going to start off with our introduction and then move on to data and EDA, followed by methods, and conclude with results and discussion. So for an introduction, natural disasters are seemingly becoming more frequent and devastating, requiring better prediction and planning. Satellite images offer vast data, but pose challenges, such as low resolution that limits human classification, um, as well as key details like buildings and infrastructure being harder to discern. And also, they take a long time to classify for humans. Our goal for this project was to make a model that is widely usable by researchers and emergence teams to make disaster classification decisions. For our implementation for this, we chose CNN because we thought it would be well suited for the task because they can extract patterns and perform edge detection, which is crucial for building damage classification. The convolution layers also provide robust feature discernment for disaster and damage assessment. Um, in the literature, you can also find similar studies that use CNNs, but for this model, we wanted to focus on accessibility and efficiency while maintaining high accuracy. The first part of the EDA that we looked at was finding image sizes and learning how we should normalize and scale images to preserve information and function well in our model. We found that the number of pictures for each disaster and looked at their size by disaster, as well as the number of damage labels. This was plotted, and we used a log transformation for better plotting. As you can see, the SoCal fire had the least amount of images, but they were also the largest in size, while the inverse is true for the Hurricane Matthew images. We decided to normalize the pictures across the disasters by 64 by 64 pixel size based on this information. We also looked into RGB differences for RGB intensities. You can see from the first set of box plots um, that the variation of RGB distribution in different classifications, and it looks like class 3 has lower pixel intensities across the board. For the second plot, you can see that the Southern California fire photos have more intensity in each color than the Midwest flooding, which is valuable information for a classification decision. Continuing on with our RGB distribution, um, you can see that on the left, RGB peaks have more area and larger bases for the California fire in comparison with the Midwest flooding. And for the Hurricane Matthew RGB distribution, green values are similar when comparing classes 1 and 3, but we can see a sizable difference between the red and blue distribution totals. And another key area we wanted to look at was the distribution of damage labels. As you can see, the Midwest flooding and the SoCal fire are skewed to the left with low distribution, while the Hurricane Matthew labels are more distributed and give a better population to train a label classification model with. And then finally, we looked at Sobel edge intensities and frequency, which weren't as informative because they were pretty similar. Cool. We'll move on to methods.
So while both models utilize a convolutional neural network, their architecture differs slightly. For task A, our binary classification model, we approach this task with a streamlined architecture optimized for distinguishing between fire and flood imagery. At its core, we have two convolution layers, each with 3x3 kernels with ReLU activation functions. After each convolution operation, we implemented max pooling layers to reduce spatial dimensions while preserving the most important features. This not only helps in reducing computational overhead, but also makes our model more robust to slight variations in input images. The two dense layers form the backbone of our classification system. The first dense layer has 12 units with ReLU activation, processing the flattened features from our convolution layers. We also incorporated a 50% dropout rate between the dense layers, which was a strategic choice to prevent overfitting and ensure model generalization. For optimization, we selected Atom Optimizer with binary cross-entropy loss, which aligns with the binary classification task. We're also tracking accuracy as our primary performance metric. And moving on to task B, which involves classifying 4 different damage levels, we significantly expanded our architecture. Here we have 4 convolution layers, still maintaining those 3x3 kernels, but with ReLU activation throughout. This deeper network was necessary to capture the subtle differences between damage levels in the satellite imagery. The dense layer configuration task B is more substantial, with our first dense layer containing 36 units. This feeds into our final layer with 4 units, corresponding to the damage level classifications. We found a 20% dropout rate after the first dense layer, provided the optimal balance for this more complex task. And task-based optimization was upgraded to Atom W optimizer and implemented categorical cross-entropy loss, which is more appropriate for the multi-class scenario. We're also using F1 score as our performance metric, which gives us a more balanced view of the model's performance across all damage levels. So both architectures were developed through extensive experimentation and validation, carefully balancing model complexity with computational efficiency. And now we'll go on to discuss the results about the classification performance. So for task A, the results showed strong performance in distinguishing between fire and flood imagery. The training metrics show consistent and robust improvements across epochs, specifically for the going into the training loss and accuracy. The initial loss started around 0.35 and steadily decreased to approximately 0.1 by epoch 12. Training accuracy improved rapidly in the early epochs as well, starting at 78 and reaching 96% by epoch 10. Going on to the validation, the loss closely tracked with the training loss, indicating good generalization. And the final validation accuracy stabilized at approximately 97%. The close alignment between the training and validation metrics suggests the model avoided overfitting, and also the narrow gap between the training and validation curves indicate a more robust model generalization.
For our task B results, we also saw some relatively good and positive looking results with our training loss quickly decreasing and our F1 score metric increasing across all damage labels. However, compared to our task A, perhaps the more complicated task that we were doing meant that we saw a bit more overfitting for the validation curve in training. You can see that the validation curve doesn't match the training loss curve quite as closely, suggesting that there's still room to tune the hyperparameters and room to prevent this overfitting and have better performance from the model. For our F1 scores, we had some interesting results where the level 1 damage classifier was overall more accurate and had higher F1 scores across training epochs, with level 0 and level 3 having similar F1 scores, and level 2 having relatively poor F1 scores that lag behind the other damage levels. There are a couple of reasons that this could be occurring. One is that the level 1 labels were higher in quantity in the original dataset, which may mean that our model had more examples to be able to determine whether there was level 1 damage compared to the other damage levels. Another potential source of confounding that could confound and create differences in the damage level classifications is the differences in how separable the distributions were, with certain distributions, such as the level 3 distribution, having less of a spread in the RGB values, which again could have made it harder to distinguish between other damage levels. Now we can move on to the discussion. So overall, our accuracy was relatively good, albeit with some clear room for improvement. For example, there was clear overtraining in task B, which means that there in the future could be opportunities to improve this model by preventing that overfitting. Additionally, further work would need to be done to ensure that this model is not biased before applying this model to other tasks or attempting to generalize them to other tasks. For example, the satellite data was only taken from a few areas in the United States, which may limit its generalizability to other geographic areas. And additionally, we didn't do work to see whether it might be biased between different locations within the United States. For example, if locations from certain socioeconomic backgrounds are not as represented in the data set. Other than that, there's a potential for the use of this model in identifying fires or assisting in search and rescue, but it would need to be paired with expert image analysis to ensure that there aren't problems with using the model. Additionally, there's a potential to try different model architectures besides just CNN. For example, we could try a diffusion model, which may be able to capture more features in the underlying data set, or even use additional data in conjunction with satellite image data, such as traditional imaging from the ground. And that should include our presentation.